Thanks everyone for joining. So yeah, I'm going to talk about a particular issue that we found, and actually, dealing with I won't talk too much about the detail of dealing with the PSERT, but we had to go through the same process, and the particular device I'm going to talk about, the company we were dealing with was equally professional. We have a lot of praise for them and how they handled the situation. So I just want to say that up front in case I forget, because Carolina made a really good presentation there. So okay, so yeah, I'm talking about a particular product, ODay, that affected a lot of devices within the IoT environment. And this was a problem because it was an embedded module which was installed in a whole lot of different systems. My colleague Gregors is not here today, but I wanted to make sure he gets credited because he was instrumental in a lot of the work that we did. So I'll do a quick intro into us. I'll talk about what the target was, the device we're looking at, what the particular issue was, and I'll actually do a demo. I'm not sure why that's not in the main list. I'm an old school hacker. I've been around 30 odd years. I'm as you can see from my current climate facial wear, I'm part of the DEF CON team. I help run DEF CON in Vegas every year. Unfortunately, virtual this year and going to be virtual again next year, sadly. Also run the London chapter. So if you're ever in London, when things get back to normal, we have a regular monthly DEF CON meet. This is my colleague, Gregors. He's based in Poland. Also works with me at a bunch of conferences like hardware.io, and we help to run the hard porn hardware hacking contest at a couple of those conferences. X-Force Red, who I work for, IBM, X-Force Red, we're Red Team pen testing services. We have a bunch of services. Again, I will skip through this because I know the time is not that long on this presentation. And my job within the team is to run our hardware labs. So this is my boss, Charles, opening our Austin, Texas lab last November, and we've got other labs around the globe. And of course, within those labs, we have sort of up-to-date tooling. And one of the things we try to do specifically is not just have like state-of-the-art, really high-end tools, which we have, but we also focus on using the kind of tools that your average attacker are going to be using. So, we think it's important to use, things like FPGAs and software-defined radios and stuff like that you're now finding your attackers are using because they're developing so fast and because it really changes the threat landscape. So it's important that you keep up to date with what literally kids in their basements can do these days, and very low cost devices. So we make sure we're up to speed with that kind of stuff as well as the very high end stuff. So let's talk about the specific target. So I'm talking about IoT modules, and in this case, we're talking about communication module. So as a lot of you presumably know, when you're developing an OT or an IoT device, you're not necessarily an expert in all of the different components that you need to build into that system. So one of the shortcuts you can take is to add a module like a communications module to your device. So you're the experts in whatever it is that this machine does. So maybe it's, watering plants or something, but you're not an expert in 3G or Wi-Fi communication. So what you do is you go out to the market and you buy a module. And these things, as well as providing those communication layers for you, they also take the load off your system. So your main processor doesn't have to think about, maintaining a 3G connection or doing a Wi-Fi connection and so on. So there's a lot of advantages to using modules in this way. But the downside to that is, as well as getting the benefits of plugging in the module, you also potentially import a bunch of third-party issues. So it might be software problems, it might be hardware problems. So the chip itself that's been utilized, or chips that have been utilized, may have fundamental issues. They may have, insecurities. They're not properly locked down, or the locks can be bypassed through, advanced techniques like glitching and so on. They may have, and very often do have, debug ports or, undocumented features that can be switched on or off by simple jumper selection or firmware tweaks. So it's really important to understand what it is you're plugging into your device. We've already talked about the different types of module, but the other thing you often get is some kind of API or some kind of communications interface, which is what you use to talk to the device in order to make it do whatever it is that it's going to do. So let's talk about the specific target. So this particular module was a 3G or 3G, 4G communications module, which included a TCP/IP stack, but it also was a sort of Java engine. So you could use it to run code in Java. And in fact, it was such a powerful chip that you could even sort of go the other way from what I was just talking about, using the module to take some of the stress off your main processor. You could actually take all of the stress off your main processor and use this thing as a main processor. So it had that much power on board. And again, I will say, this is a module being shipped and developed and maintained by Thales, and they were extremely good about their handling of this incident and dealing with the remediation and so on. So the issue itself, basically, when we looked at the module initially, it's kind of a black box. You don't know exactly what's in there. But if you took the lid off this thing, inside was a bunch of different chips. And this is common on a lot of modules. So it's kind of dressed up to look like a single chip, but actually, if you lift that tin lid off, there's a whole load of different things going on in there. So in this case, we've got flash chips, we've got modem chips, we've got MCUs and so on. So quite a complex beast under the lid. And the issue there is, that each of those chips may have its own problems. On top of that, the way the chips talk to each other may actually expose some vulnerability that otherwise wouldn't exist. If it was all inside one piece of silicon and you couldn't get to the communication channels, then it would be much harder to exploit. But in this case, and also potentially you can just take the chip off and read the memory if it's a flash chip. In this case, that's a BGA, so a bit more work than normal, but can still be done. So that wasn't the problem. We weren't attacking the hardware, although we did find the problem by attacking the hardware and then reading out the flash memory and analyzing it, and then realizing that actually there was a much simpler path once you knew how this thing worked. And that was the API for talking to the device. So what they do is they use a USB serial UART, and you send this thing's AT command. So if anyone's familiar with like Hayes modem protocols, that's an AT command. So everything was wrapped around AT commands. So all we had to do was find the TX and RX UART pins, connect to those, and we had full access to the underlying system. So here I've got a shell open, and I've got one of these devices plugged in. So I've written a little Python tool called Hayes tool, which gives me a bunch of commands that I can use to just abstract those AT commands. And so the first one I would use normally. So I've specified which serial port to talk on, and it says I'm talking to this Centurion EHS8. I can ask for a bit more info. So if I say info, I can see which hardware revision it is. So it's an EHS8 revision and IMEI and so on. Now, as I mentioned, this is a very powerful chip, and it includes this Java engine. So one of the things you can do is install Java applets into the file system on board. It's got a flash file system, and actually execute those applets. So the first thing you want to do is actually look at the flash file system. So if I do an FFS listing, so if I run FFS, and they use like floppy disk abstractions for the device names. So here you can see we have a file system called A:, and in it, all we've got is a subdirectory called public, and I've put a few files in there just to show there's something there, and you can actually see what that data looks like. The other thing you can do, as I say, is install your Java applet. So what I'm going to do is copy a jar file across. So if I use this ffs write command, so I'm going to do a hello world app sitting here. Hello world. Copy it to same name. So that's copying the jar file onto the flash file system. Should only take a few seconds. So that's completed. If I do my directory again, you can now see hello world.jar is there. So what we now want to do is install that. So we're going to say ffs install. And so what that's done is an internal process to move that jar file, well, not to move it, to copy that jar file into a hidden secure store in the flash file system that only the Java engine can access. So if you're familiar with Java, you'll know that it's very easily reversible back to source code. So the last thing you want is that your source code, your jar, is exposed and anyone can just come along and read out that jar file. But it's, even though we've installed it, if I now look at the directory, it's still there. So I want to get rid of that. So I'm going to do an ffs del, which will delete it. So I've deleted it now. If I do a directory again, you can see it's gone. But one of the commands I can issue is to look at what they call midlets. So this shows what Java modules are installed and available and will run on the system. So if I run the midlet command now, we can see we've got an installed midlet of a:hello world.jar, which is the thing I just installed. So even though it's not visible on the file system anymore, it is there and it can be executed. So now here's the problem. So we found that there is a very simple kind of backdoor built into this device that allows me to access that secret secure location. So if I actually obfuscated it, but it is now in the public domain. So if you go and read the full disclosure we did on this, you can see how this operates. But if I just run the command exploit, excuse me, that will create the parameters needed in order to see the internal hidden file system. So now here, exposed in all its glory, is the internal secure store of this module. So this is stuff that we should never get access to. It's specifically designed as a secure store. So you know these files, these jar files, should not be visible ever to end users. And even though it's lost its name, so hello world.jar is now called 00004.jar, and I can tell that by the file size. So this number on the left is the size of the file, 44605 bytes. If I look at my hello world.jar, there's the original 44605 bytes. And I can copy all of this. I won't do it because it's actually very slow. If I tell it to copy now, it'll take a good 10 minutes probably to actually copy everything across, and you don't want to sit while I do that. But if I have a look at my current directory, you can see I've already done this. And here are the files sitting on my local file system. I've just pulled them across. And probably the most interesting there, apart from the jar, which is your entire application, which is bad, is, where is he? This guy, main.ks. Now that's a Java key store. So basically, if you had used the built-in Java key management functions, provided by Java, all your private keys, public keys, whatever you decided to put into your key store, are sitting in that file. So if your application, if this is sitting in a module that is providing communications back to a backend or to a database or to a VPN or something, and you have private keys that enable that connection, they're going to be sat right there in that key store, and I, as the attacker, can just download it and read it out. So this is what we call bad. That's pretty much it for the demo. Remediation was dealt with at the time we first published this. Basically, as I say, Gemalto/Talis implemented a program to make sure all their clients were aware. And there was actually a CVE published. If you want to go and look it up, it was 2020-15-858. And we've also published a blog on the IBM knowledge base, which talks about the specific details of how this device was exploited. Now, the scary thing is, we found it on the EHS8 module, but in fact, it also affected all of these, so the 5, 6, and 8, as well as these different models, PDS 5, 6, and 8, ELS 61 and 81, and PLS 62. So it was a huge number of devices, I believe, literally in the millions of installed devices with this issue. So yeah, quite a bad vulnerability.